Hello everyone. So in the last session we have gone through a flow network, one example of a Ford-Fulkerson algorithm. Now in this session we'll see more examples of Ford-Fulkerson algorithm so you can understand how to calculate the flow value from the network. So my screen is visible to all, I think. Yes, can you see the screen now? Yes, I have shared my screen. Okay, so here we have this example. We have source node and the terminal node. And we can start from any edge, either S to A, S to B, or S to C. So here I will consider the first. So I will consider S to A to D, and D to T. So I'm going to consider the first edge as S to A to D, and D to T. It is my first augmentation path, S to A to D, and D to T. So can you tell what will be the value of the flow? How much flow will be generated in the forward direction? It is 3. Yes, absolutely. So we are getting the flow value as 3. Still I have 5 capacity left on the edge, S to A. So because of that 5 capacity, again I will select S to A. Now I have utilized A to D already, so I have to consider A to E as the second option. So I will consider S to A to E, right? S to A to T, T to E. Sorry, S to A to T, A to E, and then T. T will be the terminal, S to A to E, and E to T. So now as a result, we'll get the new flow value, which is the minimum of all these three. That is 5 as 8. You get the flow as 8, our input to the terminal and from source also. Clear? Now this is already utilized. We utilize S to A complete. Now go for I can utilize E to D. I can take and D to T. So S to B, and you can take any path. Final value will be same. We'll start with S to. We have S to B. Then from B to E. Then from E to D and D to T. S to B, B to E, E to D, and D to T. So I am able to use the minimum value as 3. Clear? The minimum value will be 3 for this path. I hope you are getting this path which I am taking. So as a result, we are getting this S to B 3, B to E 3, the flow value E to D 3, and D to T. That is now 6. And now you can see from E there are 2 outgoing arrows and both are fully utilized. From E there are 2 outgoing arrows, E to D and E to T, both are utilized. So now from S to B and B to E, E to E, and E to F and F to T. S to B, then from here E, from E we'll consider F, and from F we'll consider a T. So S to B, B to E, E to F, and F to T, if we'll consider this path. So the minimum value if I consider, then it will be 3 because S to B is 4, B to E is 3, E to F is 4, value we'll get is 3, right? That is the new augmentation. So that's what we can consider here. We have utilized that. Still you can see in S2B we have one capacity left, right? We have one capacity left, but B2E is already utilized. So we have to consider another outgoing arrow from node B. So I can consider from B to 5, and I can take C to E. So that will be the path which you can use. S to B, from B will go, from E will go to F, and from F we can go to T. So we can have the capacity. The flow value for this big one lab, that's 7 is to C. 6 1 is utilized out of 7. Six is the residual capacity. E to F we have utilized fully. So now you are utilized. You cannot go T. You cannot go to from. So now S outgoing flow. You have to outgo C to E. And is it clear? From you have a capacity 4. Now from C we have two outgoing arrows, E and F. But if I go to E, I cannot proceed further. If I use a C to E path, then I cannot proceed further because we have it only. We have to consider C to F only. So S to C, C to F, and F to T. So that's what we'll consider. S to C, C to F. S to C, C to F. C and F to will be consider. So I think it is it will do this. Right, capacity will be 2 in this. So once again, I need to share the screen with you. So I hope it is visible, right? Okay. So we are just working on the last one, S2. C2F, F2T. And this is giving here. So we are having a flow value generated by this one is 2. So now as a result, we are getting this one. Now you can check that from F, if from S, if you proceed further, right, then from S you can go to S to A is fully utilized, S to B is already utilized completely. Now S to C, if I reach to C, then there are two outgoing arrows. One is C to E, but again E is fully utilized. You don't have any another capacity left at node E. Similarly, from S to C, when you reach, then C to F, it is already utilized. It is already utilized. So now you can see there is no more addition of flow is possible. Yes, so this 17 will be the highest flow value for this flow network. Is this clear? Any query in this? So this is how you can find the network flow value, and now no more flow is possible. Now we have one more example. We have to find out the flow value. So can you identify the flow value for this network? Then we'll go step by step. Yes? Try out by your own first. First you try out, then we'll see the value. Now I want answer from you. Can you find out the total flow value of this graph? So one answer which I got from your side is 60, 60. So you can write your answer in your chat window, right? So others can see if anyone can get more than 60. Or it is 70. Anyone who is getting 70 as a flow value? Okay, so let us see the solution step by step. First path we'll select is S to A to D, D to G, G to T. That will give you 20 because all the values are 20, right? S to A to D, D to G, and G to T. So we are getting the initial value as 20. Now similar to that, we'll select another path, S to B, then B to E to H, and H to T. We are getting another path as S to B, B to E to H, and H to T. Again, the minimum flow value, right? The maximum flow value by this path is 20 because S to B capacity is 30, B to E capacity is 20, E to H capacity is 20, and H to T capacity is 30. So we are getting the value as 20, minimum of all four. So that is 20 as the new flow value. So 20 plus 20, total flow value will be 40. Now, next path we'll select is S to B, S to B, then B to A to F, F to H, and H to T, which is a very complex path. So I'm writing in the chat window. You can see that as well. S to B, B to A, S to B, B to A to F, F to H, and H to T. It is a valid path, which will give you a new flow value as 5. Yes? Screen is not visible. So S to B, B to A to F, F to H, and H to T. So this will give you a new flow value as 5. So total flow value so far will be 45. Clear? Now further, let us add the path S to C, C to F, F to H, and H to T with a flow value as 5. So you can see that we are completing the each and every flow value one by one. So S to C, C to F, S to C, C to F will consider S to C, C to F, F to H, and H to T with again flow value as 5. So that is how we'll get this 50. Next is we'll have S to C, C to F, F to okay, S to C we have taken, then C to F, then F to H, H to I, and I to T. Is it clear? That is a new path. S to C, C to F, F to H, and H to I, and I to T. That's how we'll get 55. And last, we have one more path. So this will give you a total value of 65. So total value we are getting in this flow network is 65. So basically, after that you can see that S2A it is fully utilized, S2C it is fully utilized, S2B 5 is left, but there is no way to use that 5 because there are two outgoing arrows from node B. There are two outgoing arrows from node B, B2A which is fully utilized and B2E which is also fully utilized. So you cannot utilize S2B, the capacity 5. Are you getting this? S2A fully utilized, so no need to worry. S2C fully utilized, so no need to worry about that. Now S2B, I cannot utilize the remaining 5 because from node B, we have utilized all capacity, B2A as well as B2E. As we have utilized both, we cannot do anything for S2B, remaining 5 capacity. So this is how you will get the total flow value as 65 in this flow network. I hope things are clear. So let us have certain small theorems we have to study now. So if you recall, this is what we have seen in the previous lecture, right? And we'll utilize this again, that f augmentation f dash u comma v for any edge which is a part of the flow network, the actual graph, f augmentation f dash is obtained by sigma v belongs to v, f of u comma v plus f dash u comma v minus f dash v comma u, and f augmentation f dash u comma v is equal to f augmentation f dash v comma u. This we have seen in the previous lecture, right? This we have seen in the previous lecture, the same slide, right? We have discussed this 4 steps, step 2, 3 and 4. Clear? So now using this concept, we'll prove a new thing, and that is what we have to learn today. So finally, we'll compute the value of f augmentation f dash, the total flow. Recall that we disallow anti-parallel edges in the graph G. There are no anti-parallel edges in the original graph. In the residual network, we have anti-parallel edges because the flow value will be the capacity in the reverse direction, right? So we have anti-parallel edges in the GF, but not in the actual graph. And hence, for each vertex V, which belongs to set of nodes V, we know that there can be an edge S comma V or V comma S, but never both. In the original graph, either we have edge from S to V. S is the source node. So there is an outgoing arrow from source to some another node, or there will be an arrow from V to S, but never both. So we'll define the V1 is the set of nodes such that S comma V belongs to E. So all the nodes which are outgoing nodes from the source node. So that is in the set V1. And similarly, we have a set V2, which is all the nodes which are incoming to the node S, to be the set of vertices with the edges to S. So we have total V1 union V2, which is equal to V. And we disallow anti-parallel edges, so V1 intersection V2 will be always 5. So now this is a general equation that f augmentation f dash S comma V, that is outflow from the source node. It is the outflow augmentation value from the source node S minus inflow to the source node. So outflow minus inflow will be the actual flow value. So we can write that instead of V, we can write V1. So sigma V belongs to V1, f augmentation f dash S comma V minus sigma V belongs to V2, because in V comma S, only the nodes of V2 are there. So we can write sigma V belongs to V2, f augmentation f dash V comma S. Now we'll further explore this line. So now we can write for the first one, sigma V belongs to V1, f of S comma V plus f dash S comma V minus f dash V comma S. Just we are using the augmentation equation for S comma V. Similarly, we'll write for another one. So sigma V belongs to V2, f of V comma S plus f dash v comma s minus f dash s comma v. Is it clear? Just we are using the augmentation equation for both the terms. Now we'll rearrange the terms. So you can see the step, that is sigma v belongs to v1 f s comma v plus sigma v belongs to v1 f dash s comma v minus sigma v belongs to v1 f dash v comma s. So we are applying sigma to all the terms, right, to the individual terms. Now we are rearranging the terms. So sigma v belongs to v1 f s comma v minus sigma v belongs to v2 f v comma s. So s comma v and v comma s, you can see we are grouping the two terms, plus sigma v belongs to v1 f dash s comma v plus sigma v belongs to v2 f dash s comma v minus sigma v belongs to v1 f dash v comma s minus sigma v belongs to v2 f dash v comma s. So now if I look at the first two terms, it will be as it is in the last step. Now I am merging the term number 3 and 4. I am merging the term 3 and 4 because both are same. Sigma v belongs to v1 f dash s comma v plus sigma v belongs to v2 f dash s comma v. So we are merging that two term and we are writing sigma v belongs to v1 union v2 f dash s comma v. We are merging the third and fourth term, union of the two. And similarly, I am merging the last two terms. So minus sigma v belongs to v1 union v2 f dash v comma s. So first and second term as it is, I am merging third and fourth term. Similarly, I am merging fifth and sixth term. So once we are getting this, now v1 union v2 is nothing but v. So I can write for all the terms, sigma v belongs to v. This I can write because for f s comma v, right, v belongs to v1. So if I add the v2 in it, if I add the v2 into it, then also the summation will be same. Because there is no edge with the value, right? Because v2 are the nodes which are having a v comma s. The flow value will be v comma s. So if I add the v2 into the first term, I am using all the nodes, then also the answer will be same. So sigma v belongs to v1 f of s comma v. Instead of that, I can write sigma v belongs to v. It will not change my answer. The reason is v1 intersection v2 is 5. v1 intersection v2 is 5. So I can write sigma v belongs to v f of s comma v. Similarly, for the second term, if I add the v1 into the second term, so sigma v belongs to v f of v comma s. It will not change my answer. It will not change my answer of the second term. So I am writing v for first term instead of v1. I am writing v for the second term instead of v2. And third and fourth itself are v. So that is how we are getting this term. So basically the first two term indicates what? The flow value. Outflow from the source node minus inflow to the source node. And the third and fourth term indicates augmentation from the source node, that is the outflow, and the inflow due to augmentation. So that is, we can say it is f augmentation f dash is equal to f plus f dash, right? It is mode. Mode means it is a value. So mode of f augmentation f dash is equal to mode of f plus mode of f dash. So this is how we can prove this small theory. Now, what is the limitation of this Ford-Fulkerson algorithm? So now here it is a very good example that when I consider the flow value, you can see the path S to U, U to V, and V to T. I can use only that path, right? That is the path which I can use. S to U, U to V, and V to T. This path I can use. So I'm using S to U, U to V, and V to T here. S to U, U to V, and V to T. So when I'm taking this, the flow value will be 1, I'm getting the flow by 1. So now, because of that, the residual graph will be generated in the second picture, right? Residual graph is generated in the second picture. So now I can use the path, reverse path, S to V, because you can see U to V direction will be your V to U direction in the residual graph. Are you getting this? That U to V in the first picture will be now V to U in the residual graph, right? Because the capacity in the U to V direction is 0. The capacity in U to V direction is 0. So the capacity in V to U direction will be 1. The capacity in V to U direction will be 1. So I can use this path S to V, V to U, and U to T, right? So I'm reversing this. S to V, V to U, and U to T. Right? So I'm taking this path. Right? I want to highlight a certain point. That's why I'm taking this path. Right? I want to highlight a point so that I'm taking this path. You can take other path also. S to U, U to T also. But I want to highlight a certain issue, which is the limitation of this algorithm. So now what will happen? Again, we are getting the path S to U, U to V, and V to T. Because now again the direction of U to V is there. Right? Again we are taking this direction, S to U, U to V, and V to T. So it is a continuous process. S to U, U to V, and V to T. Again the flow value will increase by 1. Again the flow value will increase by 1. So you can say what will happen? That U to V, again V to U, again U to V. This will be a continuous process. This will be a continuous process. So basically what will happen, that we can increment the flow value 1 in every iteration. We can increment the flow value only 1 by taking this path in every iteration. Is it clear? So because of that, what will happen? That we have to do number of iterations equal to the flow value, the maximum flow value, because minimum increment will be always 1. The minimum increment by the flow value will be always 1. So because of that, we have to do the number of iterations equal to the maximum flow value, right? So you can see that that is the limitation of this Ford-Fulkerson algorithm. You can see that value is very high. Your value is 1 lakh. It is 10 lakh. The value is 10 lakh from S to T. And similarly, another value is S to T via V. It is also 10 lakh. So we know that total flow value is 20 lakh. The total flow value is 20 lakh. Clear? The total flow value in this particular flow graph is 20 lakh max flow value. 10 lakh from S to U and U to T. And another 10 lakh from S to V and V to T. So we have total flow value as 20 lakh in this particular example. But if you follow this path, S to U, U to V, and V to T, or S to V, V to U, and U to T, then the number of iterations, because this path will be selected automatically by the algorithm. Algorithm will automatically select any one path, any augmentation path. So what will happen? That you have to do 20 lakh iterations to get a solution, which is a very slow algorithm, because it depends on the flow value. Because it depends on the flow value. Is it clear? The point which I am highlighting. Because augmentation path will be selected automatically. So if this path is selected, S to U, U to V, and V to T, and reverse S to V, V to U, and U to T, one by one, then we have to do 20 lakh iterations to get the max flow as 20 lakh, which is the correct answer of this. So that is the limitation of this Ford-Fulkerson algorithm, that because it depends on the augmentation path which is selected automatically by the algorithm, because you don't have to specify in a very large network which are the paths. Automatically through a DFS or BFS, through depth first search or breadth first search, it will automatically select the augmentation paths and it will generate the output. So that is the main limitation of this Ford-Fulkerson algorithm. So now if I consider this, analysis of this Ford-Fulkerson algorithm, I can say, in practice, the maximum flow problem often arises with integral capacities. If the capacities are rational numbers, we can apply an appropriate scaling transformation to make them all integral. So this Ford-Fulkerson algorithm we can use with integral capacities. So you have to do a necessary transformation to convert a rational numbers to integral. If F star denotes a maximum flow in the transform network, then a straightforward implementation of this Ford-Fulkerson executes the while loop of line 3 to 8 at most mod of F star times. Since the flow value increases by at least 1 unit in each iteration. That is what we have seen. Right? So this is our algorithm. So you can see that line number 3 to 8, which is finding a path. Line in number 3 to 8, which we have seen in the last lecture also. Finding the augmentation path. If there exists a path P from S to T in the residual network. So this 3 to 8 will execute at most F star time. F star is the maximum flow value. Right? All these lines will execute F star time, where F star is the maximum flow value. Since the flow value increases by at least 1 unit in each iteration, always you will get an increment of 1. It will never be 0 or negative. Every iteration will increment the flow value. It will never decrement. It will never remain constant. Right? And that increment will be at least 1 unit. So we can say that the while loop of line 3 to 8 executes at most F star times. So if we consider the total time complexity of this Ford-Fulkerson algorithm, then if we use depth first search or a breadth first search, if we use depth first search or a breadth first search, time to find the augmenting path will be linear. It will be always linear. Therefore, it will be equal to big O of E, because sometimes your path will include all the edges of the graph. The augmentation path will include all the edges from the source node to the terminal node. So the time is equal to big O of number of edges in the graph. And this is for one such iteration, for one augmentation path. So overall running time of the algorithm will be big O of E into mod of F star, because you will get one increment in each iteration. The number of iterations will be equal to the max flow value. And to find each augmentation path, you have to use all the edges of the graph at most. So E into mod of F star will be the time complexity of this algorithm. Is it clear? So it is big O of mod of E into F star. So that will be the time complexity overall of this algorithm. Yes, is this clear? Any query in this slides? Limitation of this Ford-Fulkerson algorithm and analysis of Ford-Fulkerson algorithm. More you practice, more you are able to get the correct flow values. It definitely needs the practice, because today you have seen that most of you have written the flow value as 60, while the actual flow value was 65. Right? So you have to practice more to get the actual flow values of the flow graph. So I think the syllabus of this advanced algorithm for the second internal is known to you. We have started with a geometric algorithms, in which we have covered the topics intersection of line segments. Then we have gone through various algorithms like a divide and conquer approach. We have gone through Jarvis March for the convex hull. Then we have gone through sweep line algorithm for multiple line segments. So that was in the intersection in the geometric algorithm. Also we have gone through closest pair of points, brute force approach algorithm. And then we have started with this flow network, in which we have discussed about capacity constraint and flow conservation property. Then we have discussed about augmentation path, a residual network, Ford-Fulkerson algorithm, its limitation, time complexity, and examples. Right? So this is what we have covered in the second internal. So in the first internal, we have stopped at a convex hull Graham-Scan algorithm. After that, whatever we have covered is in the second internal. Right? The last topic of first internal was Graham-Scan algorithm to find the convex hull. Clear? So all the best. Thank you.